Ever wonder how a battery actually works? Like, what's happening inside that little cylinder? Well, today, we're going to tear that idea apart by tackling a classic electrochemistry problem. We'll break it down step by step and see exactly how chemistry creates electricity. Let's jump in. Okay, so this is what we're up against. This is a galvanic cell, right from our source material. And yeah, at first glance, it looks complicated. You've got beakers, wires, weird solutions, but trust me, by the time we're done here, every single piece of this, especially that little question mark, is going to make total sense. We're going to solve this puzzle together. And here's how we're going to do it. This is our game plan. First, we'll figure out what all these parts are, then we'll get into the actual chemistry. After that, we'll learn a cool chemist shorthand, find some key numbers, and finally, calculate that voltage. Sound good? Let's do it. So, first things first, what even is a galvanic cell? Well, you can think of it as a device that's really good at one thing, turning the energy from a chemical reaction directly into electricity. Honestly, it's just a battery, but stripped down to its bare essentials. So let's do a quick tour of our setup. Over on the left, we've got our anode. It's a solid piece of gallium, and its job is to give away electrons. On the right, that's the cathode, a platinum electrode, which is where those electrons are headed. Now, the platinum itself is inert. It's just kind of hanging out, providing a landing strip for the electrons. Both electrodes are sitting in these special solutions full of ions. And see that thing connecting them? That's a salt bridge. Its job is to keep everything electrically balanced. The wire gives the electrons a path to travel, and that voltmeter up top, it's just waiting for us to figure out what number it's supposed to show. Right, so where does this flow of electrons actually come from? It's not magic. It's all driven by two different chemical reactions happening at the same time. One in each beaker. This, right here, is the real heart of the whole process.
To really get what's going on, you just need to know two key terms. First is oxidation. That's what happens at the anode, and it simply means losing electrons. The second is reduction, which happens at the cathode, and it means, you guessed it, gaining electrons. A super easy way to remember this is the little phrase oil rig. Oxidation is loss, reduction is gain.
So let's look at the anode, where the oxidation is happening. We have solid atoms of gallium on that electrode. What happens is, each one of those atoms gives up 3 electrons. Bam! Just like that. And in doing so, it turns into a gallium ion and dissolves into the solution. Those 3 electrons it just ditched, they're now free to start their journey through the wire. So those electrons zip through the wire and arrive at the platinum cathode. Waiting for them in the solution are these tin ions, specifically SN4+ ions. As the electrons arrive, the tin ions swim up to the electrode and each one grabs 2 electrons. This reduces them to SN2+ ions. Remember, the platinum electrode isn't part of the reaction. It's just the meeting place for the ions and electrons. Okay, let's put it all together. To get the big picture, we have to combine our 2 half reactions. The only trick is, the number of electrons lost has to equal the number of electrons gained. Gallium loses 3, but tin only gains 2. So what's the common multiple? 6. That means for every 2 gallium atoms that get oxidized, 3 tin ions have to get reduced. This final equation shows you the whole chemical story of our little battery. Now, you can probably imagine that drawing that whole diagram every single time you want to talk about a battery would get old fast. So chemists came up with a kind of secret code, a standardized shorthand to describe any galvanic cell. It's called cell notation. And it's actually a really simple code once you see it. The rule is anode stuff always goes on the left, cathode stuff on the right. A single line means you're crossing from one state to another, like from a solid electrode to a liquid solution. And that double line right in the middle, that's our salt bridge. Easy, right? So if we apply those rules to our cell, this is what we get. Let's just read it from left to right, like a sentence. We have our solid gallium anode, then a phase boundary into the gallium ion solution, then boom, the salt bridge. On the other side, we have our tin ion solution, another phase boundary, and finally, our solid platinum cathode. See? That one line of text tells you everything you need to know to build the cell. It's pretty cool. All right, we've totally nailed the chemistry part. Now it's time to figure out that voltage. To do that, we need to know the electrical push that each half reaction has. And luckily for us, the source material gives us some experimental clues to figure that out. So the source tells us that our 2 half cells were tested against a universal benchmark, which is called the standard hydrogen electrode. You can just think of it like a universal ruler. By comparing everything to hydrogen, we can get a standard measurement for any half reaction. So clue number 1 is for our gallium reaction. Its standard reduction potential is negative 0.56 volts. Now that negative sign is super important. It's telling us that gallium is less likely to be reduced than hydrogen. In fact, it would much rather be oxidized, which is exactly what it's doing as our anode. So this number confirms we've got it in the right spot. And clue number 2 is for the tin reaction. It has a standard reduction potential of positive 0.154 volts. The positive value tells us the exact opposite story. Tin is more likely to be reduced than hydrogen. It really wants to gain those electrons, which makes it a perfect cathode. Okay, this is it. We have all the pieces of the puzzle. We know the chemistry, we have the electrical potential for both sides. It is time to put it all together and finally solve for that question mark. Let's calculate the voltage. And you know what? The formula is surprisingly simple. The total standard voltage of the cell is just the potential of the cathode minus the potential of the anode. That's it. It's the difference in electrical pressure between the two sides that makes the electrons flow. If the final number is positive, it means the reaction will happen all by itself, which is the whole point of a battery. So let's plug in our numbers. We take the cathode's potential, that's positive 0.154 volts, and from that we subtract the anode's potential, which is negative 0.56 volts. And of course, subtracting a negative is the same as adding a positive. And there we have it. The standard potential of our galvanic cell is positive 0.714 volts. That question mark is officially answered. Now, this is the voltage you'd get under standard conditions, which is basically just a lab baseline. It means all your solutions are at a specific concentration and the temperature is 25 degrees Celsius. It's just how scientists make sure they're comparing apples to apples. Now, our source material throws in one last little twist. It asks, what happens if the concentrations aren't standard? What if they're different? Well, changing the concentration of the ions actually changes the electrical pressure, which changes the final voltage. We're not going to dive into the deep math for that today, but it's a really important reminder that in the real world, a battery's performance isn't always a fixed number. So let's just zoom out for a second and look at what we just did. We started with this really intimidating looking diagram, and we just took it apart piece by piece until we found the answer. We followed this really clear logical path, right? First, we figured out what was losing electrons and what was gaining them. Then, we translated that whole process into the chemist's shorthand. We acted like detectives and used experimental data to find the potentials. And finally, we used one simple formula to get the final voltage. This exact process works for pretty much any electrochemical cell. But why does any of this matter? Because this principle, this controlled flow of electrons released by a chemical reaction, that is exactly how every single battery works. The one in your phone, the one in your TV remote, the one in an electric car. It's all the same fundamental idea, just with different, more complex chemicals. So I'll leave you with one final question to think about. Based on everything we just saw, what do you think is chemically happening inside a battery when it finally runs out of juice and dies?